So thank you very much, Lucas, for the introduction, and thank you everybody here to attend the Congress. It's a great pleasure for me to be talking in this special occasion, this special edition of the Colóquio. And thank you, Jaime and Lucas, for the invitation. As you have said, this talk is going to talk about elliptic linear Weingarten surfaces, and this is a joint work with my friend João Paulo dos Santos from Universidade de Brasília. Well, let me start. I think it's not okay. Now it's working. And this is briefly the scheme of the talk. I will start giving a brief introduction about elliptic linear Weingarten surfaces and isolated singularities of some elliptic PDEs. And after that, I'm going to present a removability criterion and an extension result for this kind of surfaces. We will study what is the asymptotic behavior close to a singular point of elliptic linear Weingarten surfaces, in the sense that we are going to analyze how is the behavior of the Gauss map close to the singularity. We will also present an existent result. We will see how to construct singular solutions of singular graphs of this kind of surfaces. And finally, we are going to give a classification type result of elliptic linear Weingarten graphs and do some final remarks if I have enough time to do that. So let me start with a brief introduction about the subject we are going to study on this talk. I'm going to talk to you about elliptic linear Weingarten surfaces. This kind of surfaces satisfy linear relation between the Gaussian, K is the Gaussian curvature, and the mean curvature. And the relation is said to be elliptic whenever this relation between the constant A, B, and C is satisfied. You can see that if you put A equal to 0, you have constant Gaussian curvature surfaces, and if you put B equal to 0, we will be talking about constant mean curvature surfaces. So in some sense, this is a generalization of this well-known type of surfaces in differential geometry. Sorry. There are many very interesting properties of this kind of surfaces. I have to mention this one, that every parallel surface of an elliptic linear Weingarten surface, if you take your surface and do a translation in the normal direction, you will have another elliptic linear Weingarten surface, of course, for different constants A, B, and C, but this kind of linear relation between the Gaussian and mean curvature will be satisfied again. Eventually, singularities will appear when you do this kind of normal translation. Another important fact is that if you have a graph, which is an elliptic linear Weingarten surface, this graph will satisfy this kind of equation here in red. This is a Monge-Ampere equation. This is kind of ugly equation. It has this fully nonlinear part, determinant of the Hessian here, coming from the restriction about the Gaussian curvature. And you also have this quasi-linear part coming from the restriction about the mean curvature. Let me talk a little bit about singularities of elliptic PDEs, since we are interested in singularities of this kind of surfaces. You can see that the equation modeling graphs of elliptic linear Weingarten type is a Monge-Ampere equation which inherits a quasi-linear part coming from the mean curvature and a fully nonlinear part. So in some sense, the quasi-linear elliptic PDEs are the trivial case for isolated singularities, because whenever the solution is more or less smooth around a singular point, at the end you can deduce that such a singular point does not exist, that the singularity is removable. That is the case, for instance, for minimal surfaces or constant mean curvature surfaces and more general divergence type equations. So this is in some sense the trivial case when we talk about isolated singularities. However, for the case of Monod-Pair equations, the general Monod-Pair equation is just determinant of the Hessian of a function plus a certain matrix, which may depend on the solution and the gradient equal to a positive function. This kind of fully nonlinear equation do admit isolated singularities. For instance, consider the most simple example that you can consider when A, here this matrix is equal to 0, and you put this function equal to 1, this determinant of the Hessian equal to 1, you can obtain solutions with an isolated singularity. Okay, this is a rotational example. Also, for instance, for the case of K1 equation, the equation of, the equation prescribed curvature equal to 1, you can find surfaces as this one appearing here on the slide, which has two symmetric isolated singularities. We used to call this kind of surfaces as peak spheres. So we don't have this kind of behavior when we allow the equation to be more complicated. I think the mouse is not working. See, now it's working. So what is the kind of result? What type of classification we expect to obtain when we are dealing with elliptic linear Weingarten surfaces? So let me put here an inspiration result. This is a result from a few years ago with Jose Antonio Galvez and Pablo Mira. We proved the following. Suppose that you fixed a certain K function. You may think as a certain analytic function which will play the role of a Gaussian curvature in a certain domain of the Euclidean space, and you fix the point. And you consider A1 the class of all canonically oriented surfaces that have such a point as a singular point, which are embedded, and whose extrinsic curvature coincide with this prescribed function K. Okay, and A2 will be the class of regular analytic strictly convex Jordan curves in the sphere. So there is a one-to-one correspondence between these two classes. In some sense, what we are saying here is that if you have an isolated singularity for the prescribed equation, you will have a limit tangent cone that singularity, which will be strictly convex. And conversely, when you fix a certain strictly convex tangent cone, you may associate the tangent cone to the unit limit normal is one-to-one correspondence. So you will obtain, you can recover a unique solution and unique surface for any K you fix. So this is the kind of result we hope to obtain, or a similar one we hope to obtain for our family of surfaces. I must say that this kind of result for the pure Monod-Pair equation, in some sense, this equation, determinant of the Hessian equal to a positive function, you may think about it as the prescribed Gaussian equation in R3. Generalize previous results concerning this equation in most simple cases, as this case here for the Hessian 1 equation, when you put here the equation, the function equal to 1, and the case for surfaces of constant Gaussian curvature equal to 1, when you put this function here constant. So this is in some sense more general, but I must emphasize that in our case, we are not prescribing the curvature, we are just assuming that there is a linear relation between the Gaussian curvature and the mean curvature. So what to expect in our case? Recall that in our case, the Monod-Pair equation is more general and most complicated, since it has this part, which is a quasi-linear part, and also this determinant of the Hessian. But in our case, these A, B, and C are not zero. The point is that for this more general homogeneous equation, this kind of result is not true in general, because we know there are solutions for the general homogeneous equation whose limits normal at the singularity, or in the same way you can talk about the limit tangent cone at singularity is convex, but not strictly convex. So this condition of strictly convex does not hold. And also there exist solutions, in particular for the case we are studying for elliptic linear Weingarten surfaces, for which the gradient blows up at the singularity. So you have a cusp, you don't have a well-defined tangent cone at the singularity. In this case, the normal becomes horizontal when you approach the singularity. So what is the result? Essentially, this is roughly speaking, it's not anything is formal here, but this is the kind of result we are going to obtain at the end of the talk. If you have an elliptic linear Weingarten graph whose Gaussian map is not well defined at the puncture, you have essentially two options. The first one is that you have a cusp, which is rotationally symmetric, or the limit unit normal will describe a real analytic strictly convex Jordan curve in the sphere. That is, as I said before, you have a limit tangent cone, which is strictly convex. And there is a correspondence, there is a one-to-one correspondence between the equator, that is the curve that describes the Gaussian map when you have a cusp, and this family of strictly convex Jordan curves, and the surfaces. So you also have this one-to-one correspondence in our case. Well, let me start with some preliminary statements. For our purpose, you can suppose that the family we are studying is this one. You can normalize and suppose this constant here equal to 1. And this is the ellipticity condition in this case, okay? Of course, you can suppose that A and B are different from 0, because when you deal with the case A equal to 0, you are dealing with constant Gaussian curvature, and this result has been already done in this paper. And when you put B equal to 0, we are dealing with constant mean curvature surfaces, and isolated singularities are removable in that case. So A and B are different from 0 for us. Some definitions. What I'm saying, what do I mean when I say that a surface has an isolated singularity? In some sense, we would say that an immersion of a puncture disk in R3 has an isolated singularity, and we are assuming here that this immersion extends continuously to the puncture, okay? And the singularity will be called extendable when X and also the normal of the surface extend smoothly across the puncture. And in fact, we will call it removable, which is something more restrictive than extendable. When it is extendable, you have a well-defined tangent plane on the puncture, but also the surface is an immersion at that point. If your surface has a singularity and this singularity is not extendable, that is, you don't have a well-defined tangent plane, not well-defined unit normal at the singularity, you can define what we call limit unit normal. The limit unit normal is the set of all the points of the sphere you can achieve when you approach the singularity by any sequence of your surface. Okay, you want to see what is the curve, what is the set that this limit unit normal describes. Okay, the first, the most important tool we are going to use to prove our results is what we call the associated Riemannian metric of the surface. It happens that since we are dealing with elliptic linear Weingarten surfaces, this quantity here, A, times the first fundamental form plus b times the second fundamental form. This quadratic form that we call ds squared is defined since the immersion is elliptic. So up to a chain of orientation, if we prescribe the right orientation and up to a chain of A, sign of A if necessary, we can assume that this metric ds squared, A times the first fundamental form plus B times the second fundamental form, this is a Riemannian metric associated to the surface. Okay, so we can consider this conformal structure induced in our puncture disk, in our immersion, by this new metric, ds squared. I mean, we are not consider the conformal structure induced by the first fundamental form, but by this new Riemannian metric associated to the surface. And what happens is that with respect to this new conformal structure, the Gaussian map is a harmonic map into the sphere. The Laplacian of the Gaussian map satisfies this equation here, which means that it is a harmonic map. And an important fact is that Galvez, Martin, and Milan proved that there is a representation formula of your immersion in terms of this Gauss map. So you can recover your surfaces or elliptic linear Weingarten surfaces in terms of harmonic maps into the sphere. Well, if you write your conformal coordinates, u and v, as a complex conformal parameter, this is the expression of the metric ds squared. Remember, this square is 8 times the first fundamental form plus b times the second fundamental form, which is conformal. Okay, we are choosing conformal parameter here. This is the expression for the first, the second, and the third fundamental form. Okay, q here is the half differential. It is a holomorphic function. Okay, and an important fact is that the determinant of the first fundamental form is a constant times the determinant of this metric ds squared. So this metric identifies the generation points of your surfaces. Okay, we can rewrite these functions here appearing this new and this row of functions in this way. We can introduce this angle function that we call omega here, this hyperbolic angle function. And we observe that the conformal factor of your metric ds squared is written in this way. And remember, you hear q, it's a holomorphic function. So at the end, what will happen is that the surface will degenerate when omega goes to 0. The zeros of q are isolated, since it is a holomorphic function. So as a spoiler, I'm going to say the degeneration points where you don't have a well-defined unit normal will correspond to a 0 of omega. Observe that when omega goes to 0, the Gaussian and the mean curvature, which are written here, blows up. So at isolated singularity points of elliptic linear Weingarten surfaces, you will have the Gaussian curvature going to plus or minus infinity. I have forgotten to say that since the metric ds squared is assumed to be Riemannian, here omega is bigger than 0. And since omega is bigger than 0, the Gaussian curvature goes to plus infinity when omega goes to 0 and A is negative, and conversely. So the sign of the Gaussian curvature is the opposite of the sign of A here. Okay, another important fact is that the Gaussian equation with respect to these conformal coordinates is written in this way, Laplacian of this angle function. This is a sine-Gordon type equation. And this constant, omega 0 that appear here, has the sign of A. Okay, so it's positive if A is positive and conversely. This equation will appear along the talk a lot. So let me start with the first result about extension of the surface, and when can we say that the singularity is in fact removable, or movability result? Well, the first observation is that by uniformization, your Riemann surface associated to this metric ds square will be conformal to a puncture disk or to an annulus. Okay, these are the two options, the possible options. When the conformal structure is that of an annulus, we will assume that up to a conformal reparametrization, you can reparametrize your surface in a certain strip. Here, the red line here will correspond to one part of the boundary of the annulus, which is mapped into the singularity. Okay, the singularity will correspond to this real line. And you are having here a 2 pi identification to cover this annulus. In some sense, what I'm saying is that you can push it here. You can consider your parameters U and V here. Take this orthogonal system of coordinates. U will be the horizontal, V will be the vertical. You have your original domain where the origin is mapped into the singularity, but you are reparametrizing in terms of these new coordinates. Here, the black line is corresponding to this boundary here, so this black line is not important. The important one is this red line that we call as R, the boundary of this strip, which is mapped into the singularity. Okay. So this is our first extension result. It says that if you have an elliptic linear Weingarten surface, which is defined, which has the conformal structure of an annulus, that is the associated conformal parameters are defined in an annulus, then it extends, X itself, the parameterization itself and its unit normal extends analytically across the boundary of the annulus. Okay, so your surface is not regular, your original coordinates are not good, since the surface is not an immersion and it has not a well-defined tangent plane. But when you consider these new parameters, everything is analytic, even across the line corresponding to the singularity. This will be important. I will do now, and spoiler is that if you have a singularity which is totally isolated, I put here this totally, in some sense, totally isolated, because when you start with a concave surface, that is a surface with a singularity that explodes, whose curvature explodes to -infinity, you have to assume that this extension that you have, that surface extends across the singularity, and this whole surface, that like this double surface, has no other singularities. Do not have curves of singularities collapsing here, for instance. So if you assume that, and you assume that the limit unit normal is not the equator, that is, you don't have a cusp, then when you start with a concave surface, its extension, is a convex surface, and conversely, if you have a convex surface with an isolated singularity, its extension across the singularity will be concave. The point is that here upstairs, you will have a positive, remember you have U and V, your conformal coordinates. Omega is bigger than 0 in this strip. Omega will be equal to 0 along the real line. You will have the degeneration of your first fundamental form. And here downstairs, omega will be negative. That means that the metric induced downstairs is not Riemannian, it's negative defined, but you can change after that, you can change properly the orientation downstairs and adapt the sign of A in order to have also a Riemannian metric associated to this downstairs surface. But this is an important fact. You have a negative curvature, you pass to positive curvature. Well, why I emphasize about the conformal structure? Why is the conformal structure important in our case? Since it will determine if the singularity is in fact removable or not. Recall that we had two possibilities, or the conformal structure is that of an annulus, or it is of a unit of a puncture disk, sorry. The point is that we can prove, we start with the case when A is negative. You can think that when A is negative, in your head you can put that we are dealing with convex surfaces. This is the case when the curvature blows up to plus infinity, the Gaussian curvature. So if you have an elliptic linear Weingarten surface with an isolated singularity, and the associated conformal structure is that of a puncture disk, all these expressions, all these conditions are equivalent, but you can focus on this fact. Then the singularity is removable, or it is a branch point. In particular, if the surface is embedded, the singularity is removable. So this is an example of the importance of the conformal structure. In the case when A is positive, that is the concave case, things are not so good. The most we can say is that the singularity is extendable. That is why I recall that extendable means that you have a well-defined limit to the normal. You have a well-defined tangent plane at singularity, but eventually your surface is not an immersion at such a point. This is the most we can say in the case A bigger than 0, and moreover, in this case, we have to assume that the area is finite. Here, that's a consequence, it's not necessary. So I'm not going to prove every detail here, every correspondence in this theorem, but I want to give the idea of the proof of a corollary. The corollary is the following. This corollary does not depend on the sign of A. This is for any A and B. So if you have the conformal structure of a puncture disk and the area of your surface close to the singularity is finite, then the singularity is extendable. The first step to prove this result is that whenever you have finite area, you can do some computations by means of the divergence theorem applied to this Laplacian here, when f is the distance to the origin, the square of the distance to the origin, to deduce that finite area implies finite total curvature. And this intermediate result, since it is important by itself, does not depend on the conformal structure for any surface, and does not depend on the same of A if the surface is concave or convex. Okay. Once you have final total curvature, this inequality here implies that the Gaussian map of your surface belongs to the Sobolev space. I'm assuming here, now I am assuming that conformal structure is of a puncture disk. Then a result about harmonic maps into the sphere by a lane implies that the surface is in fact extendable, that n in fact extends smoothly across the singularity. So as you have a representation in terms of n, x also extends smoothly across the singularity. Why can we say a little bit more when A is negative, that is when the surface is convex? That is because when A is negative, this equation, the Gaussian equation for your surface implies that omega is a superharmonic function. It is a positive superharmonic function, and you have the conformal structure puncture disk. So you can apply the maximum principle in a proper way. You can take an exhaustion of annuli and do some computation and deduce that, in fact, at the puncture, the angle function is positive. So since it is positive, and by some result about harmonic maps into the sphere by Wood, you will have that, in fact, or you don't have any singularity at all, the singularity is removable, or you have a branch point, but this case is impossible in the case of embedded surfaces, okay? Well, let me now talk a little bit about what is the asymptotic behavior of your surfaces when you approach a singularity. How is the behavior of your limit unit normal? What is the behavior of the normal when you approach? You don't have a well-defined limit normal because it's not extendable. I mean, the limit normal is not a point. If it were a point, that means that you have a well-defined tangent plane. It is not a point, but what it is, what kind of curve does it describe? That is the point. Well, this is the key definition. That is the behavior of the unit normal in the more general situation. We will say that a curve in the sphere is called a locally strictly convex curve with admissible cusps if this relation between this product of the norm of the velocity of the limit unit normal times its geodesic curvature is different from zero. What I'm saying is you have two options. At the points where the curve is regular, the geodesic curvature is different from zero, but you admit these points, these bad points that we call cusps, which are points where the curve is not regular, that is, this may be zero, but in this case, the geodesic curvature must blow up. Okay, this is something to have this sphere. This curve will be something like that. You have points where you don't have eventually a well-defined tangent vector and the geodesic curvature explodes. Okay. So this is the result that we obtain. If you have an elliptic linear Weingarten surface with a non-extendable finite isolated singularity, I will make a break here. I assume the singularity is non-extendable and finite to use the previous result to assume that the conformal structure induced by this metric is that of an annulus. So this immediately implies that you can reparameterize your surface with respect to these conformal coordinates U and V, which are defined in a certain strip. So if this is the case, then the limit unit normal is this kind of curve. This is a locally strictly convex curve with admissible cups in the sphere, or it may be a great circle, a geodesic on the sphere, if the geodesic curvature is identically zero. Okay. As a corollary of this proposition, we deduce that if X is in fact embedded, if it is a graph, then the limit unit normal is or the equator, that is any equator, after rotation you can assume is the horizontal equator, or it determines a real analytic regular, in this case is regular, if the surface is embedded, is regular, a strictly convex Jordan curve, that is an embedded curve. The limit unit normal is better than this locally strictly convex with admissible cusps. These cusps may not appear in this case. So I will skip the details, but I want to mention what is the proof of the proposition. How do deduce this kind of behavior about the limit unit normal? The key point is this relation here in red. You have your strip where your surface is now parameterized. This red line here corresponds to the singularity. You have your angle function, which is positive in the strip and is 0 on the boundary. And the normal derivative, this is V and this is U. V is the vertical direction. So the normal derivative along this quality is along the real line, okay? The normal derivative of omega along the real line is the product of K, the geodesic curvature, times the modulus of the velocity, okay? So if A is positive, you have a suppose that omega is a positive superharmonic function. So Hopf's lemma implies that this transversal derivative must be positive. And so this quantity here is positive, which is essentially the definition of an admissible cusp. And when A is negative, you have that now the inequalities here of omega and the Laplacian of omega points in the wrong direction. I mean, omega is positive, but it is a subharmonic function. In that case, you have two options. Or omega v is identically 0, or it has isolated points, or isolated 0, sorry, because of it is an analytic function, a real analytic function. If omega v is identically 0, it means that you are on one great circle, you are on the equator. If not, you will only have isolated zeros, and you can apply now again Hopf's lemma, but now you apply it to the reflected surface. You apply it downstairs where omega will be negative. In this part of the proof, we are assuming that the reflected surface does not have singularities collapsing here. You don't have curves of singularities collapsing here. That is, that the reflected surface has also an isolated singularity. Okay. Okay. We can also construct isolated singularities by means of the Cauchy problem for the harmonic map N by putting this initial condition here. I'm not getting into details, but if you start with a curve on the sphere which has cusp, admissible cusp, you will have an isolated finite singularity. And if the curve that you start with is a strictly convex Jordan curve, in fact, the surface that you construct is embedded, and a certain orientation on the curve inherits the canonical orientation on your surface. I'm not entering too much into details. For the case when the slope is bounded, this proof was already done for more general modular equation in the previous work. So to finish, I will give the classification of graphs. And I want to formalize the definition of a cusp. We will say that a graph here, and I'm assuming I will give the details what I mean as a graph, in fact, is a bigraph. We say that a cusp, that a surface is a cusp whenever the slope becomes vertical when we approach the singularity, and what we prove is that all cusps are rotationally symmetric, okay, as when you assume that the surface around the singularity is embedded. The proof is the following. You first prove that if you have a cusp, the limit to the normal is the equator, that is, the unit normal of the singularity covers, is always horizontal, covers one equator, and since this limit to the normal is rotationally symmetric, the surface that you started with must be rotationally symmetric. The point is that you can explicitly determine this kind of surfaces because parallel to any elliptic linear Weingarten surface, you have always a constant Gaussian curvature convex, a constant positive Gaussian curvature surface. And rotational, this kind of rotationally K equal constant surface, you can rescale and suppose that constant is equal to 1, are completely classified. So you can completely classify cusps. So if you put together this instant result that I have present before and all the asymptotic study we have done previously, you can enunciate the classification, which is something like that. If you have an elliptic linear Weingarten graph with a non-extendable isolated singularity at the origin, you consider this class for fixed A and B, and you consider A2 the class of regular analytic, strictly convex, negatively oriented Jordan curves in the sphere, joined with the equator. This case will correspond to the cusps. Then the map that sends to each surface its limit to the normal gives a one-to-one correspondence between these two classes. Okay, I have to mention that in the case the slope is not bounded, these graphs here are in fact considered as bigraph. We are assuming that the reflected surface is also embedded. And some remarks, other remarks to finish. I think I'm almost done. I am written here not extendable since at the beginning, if you remember, in the case when A is positive, that is in the concave case, we cannot prove that the singularity is removable if the structure is that of a puncture disk, because we don't know if there exists non-removable isolated singularity of this conformal type. So in this case, of course, they are concave and non-extendable, but if they don't exist, you can replace here non-extendable by non-removable, and everything is the same. In the case, of course, in the case A negative, you can put here non-removable because everything is non-removable if you assume, everything is removable if you assume this conformal type here. So sorry for the delay. Thank you very much for your attention.